now we have Everett and Victor from 8565 presenting auto aim and distance estimation using TensorFlow. Take it away.
Hi everyone. So there are many capabilities that TensorFlow has if you do it right, and we're going to be presenting two of the most advanced yet also useful ways. So these are auto aim and distance estimation. So a little bit about yourself.
Okay, I'm Everett. I am a rising ninth grader and I do programming.
I'm Victor. I'm a rising ninth grader, and I actually do hardware, but I wanted to try software. So that's my So a bit about the agenda today. We're gonna go over auto aim first, and then we're gonna go over distance estimation. We're gonna go over a simple way to do distance estimation, and then a really comprehensive way.
Okay, so the main goal of why did auto do that? Okay, that's cool. The main goal of auto aim is that if we have like a cue and it's to the right of our camera's field of view, and we want to put it directly to the center. So how we do that is we put a servo below our camera that turns it kind of like how you turn your head. So like if Victor's on the right side, I go like whoop, and now he's in the center. So yeah. Step one, we find all our coordinates of the stuff. This can be determined from like all the bounding boxes and whatnot. And then we determine our error. Basically, where is Victor on my camera's field of view right now, and where do I want it to be? And then, but then we correct the error. And yeah, using like kind of normal control or like the typical stuff, the servo can be kind of wobbly. So which is why I decided to randomly learn PID during the summer. Yeah, so the reason my PID is better is because it's more precise and it takes in 3 factors to produce 1 output instead of the usual 1 factor, 1 output. Yeah, so ignore the text. Basically what like proportional does is it's like it determines how fast you go towards 0 error. Like directly proportional to the error, as like the name suggests. So if you have a lower P, you go slower towards 0 error. Then we'll go to derivative. Basically what this does is it controls that, it makes sure that your program isn't responding too quickly. Kind of like a person like skating on an ice rink is harder to control than like a person walking on land, I guess. And then integral just deals with like constant errors. If your servo has some sort of like friction stuff that's being annoying, that's what that fixes. Yeah, that's the code snippet. It's not really too complicated. Okay, this is like the demo I recorded at my home. Yeah, there's not a ton of wobbling, though there may be a little bit, like, yeah, like right there. But overall, it's pretty nice. Oh, stop playing. Okay. And now we'll move on to distance estimation. Yeah, basically, all this slide wants to say is if you want to do some calculations of the camera, you can always do it in terms of similar examples. Okay, so what we want to do with distance estimation is if you have a object that's in your camera, I want to know how far away is it from the camera. And the first way we do this is kind of more intuitive. It's like the first thing you think about when you do distance estimation. It's like as an object goes further, it's like inversely proportional. I mean like what am I saying? As the object gets further from the camera, like the width/height is like inversely proportional, I guess. So we first determine all the variables. We'll get to this later. And then we use magic formula. And basically, all this is it's combining 4 factors: perceived focal length, width in pixels, the actual distance from the camera, and then the actual width. So you do need to know what object you're detecting. Like if it's a cube, I know that it's like 2 inches wide. And then by rearranging this equation, we can get a equation that says what the distance is from the camera. And the only thing we really need is the width in pixels, because we already know the actual width, and then f is a constant determined through like experimentation. And yeah, so on the left, it's like a calibration image that I use to determine F. Like it's exactly 12 inches away from the camera. And then to test it, I use it on the right image. It's like a bit further from the camera. And it says it's 7.5 inches away, which is kind of close to what I had. So yeah.
Okay, so there are actually many ways to do distance estimation. What Everett just showed you is one of the easiest ways to do it. However, it's not really comprehensive or general because it has to rely on auto aim and the camera needs to be, and the object needs to be in a specific orientation. So now this is the simplest way I can put the most comprehensive, robust, and general way to do distance estimation for almost any kind of thing you want to do. So to explain this, we'll start off with a small sketch. So basically, on your screen, you have a camera frame. And your camera frame, you can see your camera frame because it goes through a camera lens that projects the field through it. And we're gonna show this projection using these lines that we can draw as rays. So you can kind of see how that works there. And using those rays, we can now draw a bunch of auxiliary stuff on our physical field. Like we can define an origin, we can define an X and Y axis, and we can do a bunch of other neat projection stuff. And we're gonna label a bunch of variables too, and these variables, as listed here, are gonna be plugged into our formulas later, so we can actually use our distance. So this Greek letter is called psi, and it's the X coordinate on the camera frame in pixels. So in other words, what you see on your screen in your camera frame, the X coordinate that you can get is psi. And similarly, eta is the Y coordinate on the camera frame, and the X is the X coordinate on the field, which is the physical field. Same thing for Y. K is the sort of amplification projection factor that you get from when you project your field to your camera frame through your lens. And finally, alpha is the camera angle. So at the end of the day, we're gonna get these two formulas to plug in for X and Y to get an accurate distance reading. That's what it looks like. And just really quickly, how we get here, we take a side view of the picture that we had before. All the variables and values still stay the same. And we just use some lob signs, some systems, substitutions, simplifications, and this is what you get. Yeah, so if I read through this, you get the physical X coordinate on the field is D, the distance from the origin of your field to your camera lens, times the cosine of alpha, which is your camera angle, times K, the amplification factor, times eta, the X coordinate in pixels on the camera frame. All that divided by D times cosine alpha minus K eta, which is the Y coordinate value in pixels, times sine alpha. And the physical Y coordinate is D times K eta divided by D times cosine of alpha minus K eta sine alpha. So you might be overwhelmed by the amount of variables we have in those equations, but the way we make these formulas work is we calibrate all of them out. And you can do this manually, or some of them you'll have to do it by code. We'll talk about that here. So we'll start simple. Alpha, the camera angle, pretty easy. You just set your camera up on the mount you want to use, and you just measure the angle the camera face makes with the ground. I just use a protractor. For D, the distance from the lens to the origin, what I did was I set the camera up and I drew a dot on a piece of paper. I opened FTC dashboard to get the camera frame view. And on the ground, I moved the paper until the dot was in the exact center of the camera frame. And then I just used a tape measure to measure the distance from the dot to the lens. And then for eta, the X coordinate on the camera frame in pixels, I just ran a simple code with my TensorFlow. And I just used recognition dot get left. Same thing for eta, just recognition dot like get top, maybe. And for K, the amplification factor, this one's a bit trickier. You have to keep the origin you use to calibrate D. You need to place a detectable object on the field, and you need to measure the distance in real life in the X direction between that origin and the object you detect. You divide that by the pixel distance on the screen you display the telemetry, also in the X direction. So when you, like, the principle here is when you divide those two correlating values, you get a ratio, and that ratio is the implementation factor. So now that all the theory is out of the way, we can just get started on our code. So since I'm like not really advancing this stuff, I try to make this as simple as possible. But basically the first step is we define all the functions we want to use. So we have our point transformations, which I should mention that in order for this formula to work, the origin that you base your detected points off of has to be in the center of the camera frame. Unfortunately, Vuforia default origin is in the top left corner. So I just apply simple shift for the X and Y coordinates to be able to get a new, better reference. And then for the point on the object that we want to use to detect, I just took the middle between two opposite corners of the bounding box to get like the best point on the image. And then we have our distance formula, which is just to apply to the formulas once you apply all of your parameters to them. And then the meat and cheese, which is just like the actual formulas that we went over a few slides ago. Again, we have all the variables we talked about, and we have to painstakingly write out the entire formula. But yeah. And then once that's out of the way, in your main loop, you just want to call all these functions in double variables. That's pretty self-explanatory. Go on. And then just display them in telemetry. Yeah, so then once you do all that, and this is what I updated the telemetry, so you can see we have the number of objects detected, we have the estimated distance, then we have the X and Y benchmarks that we use to run a formula through. Then you have the X and Y physical coordinates on the floor. And so when I tested this, like, it was generally sort of accurate. It would get within like 1 or 2 centimeters. Like, it would get within 1 or 2 centimeters. There would be some like really weird spots where it would spike crazily and it would not be accurate at all. But that's because of the downside of using this sort of method to do distance estimation, because there's so many values that need to calibrate. And if you like don't get any of them accurately, it's gonna potentially screw up what you output. But I think I got close enough, and we have, I would say, like pretty good results.
Okay, so we just presented 2 distance estimation methods. There's one simpler one, and then there's one more complex one, but like which one should you use? Well, I guess there's no real answer to that, I guess. Mine is like the one I presented. It's more simple, it's more intuitive. But it's like when an object is more towards the side of the camera, it gets less and less accurate. So if you're only doing like, I guess, I wanna see this cube's position relative to the other ones, maybe you just use like the simpler one. And then Victor's is just if you want like precise results, I wanna know how far these 4 cubes are from the camera. And if you tune it properly, it can give you really, really good results, because it's a really creative method of doing distance estimation. Okay. That's it.
Does anyone have any questions? I guess not.
Is this for autonomous only, or is it, did you use that with teleops as well?
So like, this was just like a sort of simple model. We just put a camera on just like a simple frame and just applied this code to it. But the inspiration for this was actually like, we had a movable intake arm, sort of, and we wanted to detect the freight that was closest to the camera to be able to intake it.
So this is just a theoretical, it wasn't, we can actually use this.
No, but this is, but like, everything from there is pretty straightforward.
Yeah, as Everett forgot to mention that, because in order to use that, it has to train a fast signal customized TensorFlow model, which can provide you a decent sample rate to do all the country reports estimation. And we also have to mention that the scenario is based on single camera distance estimation.
Yeah.
If there was 2 cameras, the algorithm is going to be different.
The processing overhead would be pretty high with
The what?
the processing overhead.
Oh yeah, so last year when we were actually using a TensorFlow thingy, we did have that issue in which like TensorFlow models are generally kind of slow and there's like a lot of lag and stuff. So the way we solved that was we used like this library developed by Google, it's like you don't run the TensorFlow model on every frame. Sometimes like it just predicts where the bounding boxes should be, like based on like your robot's movement or velocity or whatever. Yeah, and that sped it up a lot.
Yeah, any more questions?
I think that's all for this. We can go on to our last presentation of the day. And then for you guys who are still around, I guess everyone else forgot that there's still another drawing.
Oh.
Can I get a ticket?
Huh?